Hello everyone, so we're going to look at trigonometric integrals, and this is kind of like a little bit of a precursor to trigonometric substitution, but we kind of need to do it just to review and look at these specialized integrals. A lot of them will be able to be done with what are known as reduction formulas that we'll look at the end, but let's go ahead and look at some examples that involve some powers of sine and cosine. So no new techniques, but we'll just evaluate some of these integrals and see how they can be done. So let's look at this example where we're looking at, let's say, either powers of sine or cosine. So let's go ahead and try to integrate cosine to the fifth of x dx. And really the trick is we know with even powers we can perform the Pythagorean substitution because sine squared plus cosine squared equals 1. So we would have substitutions for, say, cosine squared, cosine to the fourth, cosine to the sixth, and so on. So if you notice that, then what can be done is we can actually think about this integral as the integral of cosine to the fourth of x times cosine of x. And we can replace that cosine to the fourth with the substitution I just mentioned. So now this will be cosine squared is 1 minus sine squared, so this will be 1 minus sine squared of x quantity squared times the cosine of x. And now this leads to a straightforward substitution because if we let u equal the sine of x, du will be cosine of x dx. So that's exactly what we're going to do. So let u equal the sine of x. So then du is cosine of x dx. So we can transform our integral, and it becomes just the integral of 1 minus u squared du. And that's just a polynomial, so we can expand that. That's probably the easiest way. We don't want to do anything fancier than that. So that's going to be, let's see, 1 minus 2u squared plus u to the fourth du. And then that has a very easy antiderivative, just u minus 2u to the third over 3 plus u to the fifth over 5 plus our constant of integration. So we can change that u back into the sine of x. So our antiderivative for the original integral is the sine of x minus 2 sine cubed of x over 3 plus sine to the fifth of x over 5 plus a constant. And that's the antiderivative for part A. Let's go ahead and do something similar with cosine. We'll start off with our original integral in terms of sine rather than cosine. So B, let's look at the integral of sine to the fourth of x dx. So again, what are we going to do here? Well, for this one, we're just going to have to, this is actually a little bit clever. So we're going to utilize some of our half-angle identities that we did before. So let's go ahead and recall those. So remember, the half-angle identities come from combining the Pythagorean identity with a double angle identity for cosine. So if you need a refresher on that, just go back to that trig video. I recalled the trig identities in one of those videos where I go over that. So that's on my YouTube page as well, so you can review that there. But basically what we have is sine squared is equal to 1 minus sine squared of x, 1 minus cosine of 2x over 2, and cosine squared of x is 1 plus cosine of x, 1 plus cosine 2x over 2. So I'll just mention combining cosine of 2x equals cosine squared x minus sine squared x and cosine squared x plus sine squared x equals 1 is where those identities come from. Notice you can just solve for cosine squared x and plug it into the first equation. So that's basically where the half-angle identities are coming from. So what we're going to do here is we're just going to replace the sine to the fourth of x with the sine, the half-angle identity that we see above, sine squared of x. And that will allow us to integrate. So a little bit of work, but we'll see how that works in a second. So, so the integral of sine to the fourth x dx using the identity above is going to be 1 minus cosine of 2x over 2 squared, because it's sine squared squared. And then we can go ahead and expand that just using algebra. So we're going to get a 1/4. I'm just going to bring that in front of the integral times the integral of 1 minus 2 cosine squared 2x. Just 2 cosine 2x. And then plus cosine squared 2x. dx. Okay, so now we've got our integral now completely in terms of the cosines. There's only one that's going to be a little bit tricky to evaluate, and that's the cosine squared of 2x. So what we're going to do is, so this one is by half-angle formula for sine. So for the next one, we're going to use the, we can already integrate the 1 and the minus 2 cosine 2x. That's not difficult. But the cosine squared 2x, we're going to use the half angle for cosine there. So what does the half angle for cosine make that? Well, we know the half angle for cosine is 1 plus cosine 2x over 2. So cosine squared, since we already have 2x, it's going to be 1 plus cosine 4x over 2. So that's exactly what the integral becomes. So we get 1/4. And then the first two terms I'm going to leave the same. And the last one I'm going to change to 1 plus cosine 4x over 4 dx. And this is by half angle for cosine. So we can just use some algebra to get this all together. Oh, sorry, it should be over 2, not over 4. That's a mistake there. Alright, so you can split apart the fraction and make it 1/2 plus cosine 4x over 2, and we can combine the 1 and the 1/2 to make that 3/2. So we now have the integral of 3/2 minus 2 cosine 2x plus cosine of 4x over 2. And each of the trigonometric summands can be done just using substitution. For the middle term, you would just let u be 2x. For the last term, you'd let u be 4x. So now we're basically ready to write down the final antiderivative. We have our 1/4 on the outside. And then we would have 3 over 2x. And then we would have, so the antiderivative, so the antiderivative of cosine is sine, and there's going to be an extra 2 coming out from the substitution. So we just have minus the sine of 2x here. You can check that by writing down the substitution if you want. And then we should have, again, plus sine of 4x. We have another 4 that comes out from the substitution, so now this is over 8. Then we have our general constant of integration. And if you want, you can go ahead and distribute the 1/4. So there's no more parentheses. So we would have 3x over 8 minus sine of 2x over 4. And then plus the sine of 4x over 32. plus c. And that is the final integral. So again, a little complicated there, how handling that even power of cosine, but we see that it can be done. And in general, we have formulas that can apply to these types of integrals because it's the same technique over and over again. So that's handling powers on their own in general. Let's look at maybe handling products of these types of trig functions. So this example, we want to handle products of sine and cosine. So let's say we're integrating sine to the fourth of x times cosine squared of x dx. How are we going to handle this integral? Well, this is going to be very similar to last time. What we're going to do is we're just going to apply both half-angle formulas to substitute for the even powers. So this is going to be the integral of 1 minus cosine of 2x over 2 quantity squared times 1 plus cosine of 2x over 2. And this is just, again, by the half-angle identities. And then, again, we just use algebra to expand everything. So you can go ahead and check, but if you write all this out, basically this simplifies to 1/8 times the integral of 1 minus the cosine of 2x minus cosine squared of 2x plus cosine cubed of 2x. And again, we're going to want to split this up in a, so we're going to split this up and use the same techniques that we did at the beginning. Namely, we're just going to be adding more identities. So let's think about this as the 1/8 integral of 1 minus cosine 2x. That part can already be done with just normal techniques, right? Integral of 1 is just going to be x, and the integral of cosine of 2x is just going to be sine of 2x over 2 from substitution. But what we're really concerned with is what are we going to do about the cosine squared of 2x term, and what about the cosine cubed term? So the cosine squared term, again, we're just going to use the half-angle identity on that, and the cosine cubed term, we're going to split to cosine squared times cosine, and then go ahead and use the Pythagorean identity and substitution. So we've already encountered these techniques. They're just all now coming up at once in the same integral. So all of these should, technically the 1/8 is around everything. So let's see, we have 1/8. And then the first integral we can evaluate, we basically already said what that is. That's x minus the sine of 2x over 2. And then the middle integral we're going to change to, 1 minus the cosine of 2. So it's a half angle, so it's actually going to be cosine of 4x now. So we're going to get 1 plus cosine 4x over 2. And then the last integral we're going to write as cosine squared of 2x, which we're going to change to 1 minus sine squared of 2x times the cosine of 2x. So that's how we get all three powers there. So then we can do substitution, right? We let u be the sine squared of x, and then du will be cosine 2x dx. We do have an extra 2 popping out this time, but it's not going to be much of an issue. So let's go ahead and integrate. Again, there's a lot of stuff to do all at once. So really what we want to do is figure out this last integral. So let's go ahead and do that. So let u equal sine of 2x. So then du is 2 cosine 2x dx. So we can replace cosine 2x dx with du over 2. So this integral right here becomes the integral of 1 minus u squared. We have the 1/2 and then du. So this will become 1/2 u minus 1/2 times 1/3, so 1/6 u cubed. So that's our very last integral there. So I just wanted to get that done ahead of time. So it's going to be sine of 2x over 2 plus sine, minus, I don't know why I wrote plus, minus sine cubed 2x over 6. So that's our very last integral. So anyway, let me try and continue all this down here. So we have our 1/8. So we have x minus sine of 2x over 2. And then we're going to have minus, the 1 over 2 is going to become 1/2 x. And then cosine 4x over 2, that's going to be sine of 4x over 8. So we have to distribute the negative, so it's going to be minus sine of 4x over 8. And then we have our last integral. So again, I'm distributing the negative to both terms for this middle integral. And then we should have plus sine of 2x over 2 minus sine cubed of 2x over 6. And then we have plus our constant of integration. So let's collect all our terms and see if everything agrees. I believe it should. So we have x minus 1/2 x, which is 1/2 x times 1/8. So we get 1/16 x. And then we have a minus sine of 2x over 2 and a plus sine of 2x over 2. So interestingly enough, this term cancels with this term. So those drop out. Then we have sine of 4x over 8 times 1/8. So we've got minus 1 over 64 times the sine of 4x. And then we have, at the very end there, 1 over 6 times 1 over 8. So we've got minus 1 over 48 times sine cubed of 2x plus our constant of integration. And that was quite an example. A lot of stuff going on there, but it's just revisiting all the techniques that we've done so far today. So in general, there are some reduction formulas. So you can derive these, but really it's just going through the patterns that we've had here. Additionally, what happens is you're just using n rather than numbers. So I will go ahead, let me go ahead and I'll pause the video and then clip those in. So here's the reduction formulas for the four major trig functions that we're looking at, that we have nice properties for. And you can see what it does is it takes an integral, say if you look at formula 1, integral of sine to the n of x, and it reduces it to a term that's already been integrated plus an integral of something with a smaller power. It actually drops by 2. So the power is now 2 lower. So what that allows us to do is perform this operation until we get to an integral of either size 1 or 2, and then we'll know how to integrate that, and so we'll have performed the entire anti-differentiation. Anyhow, let's work through an example using one of these reduction formulas. And in general, you're not going to have to, if you run across one of these integrals, you don't have to think too much. You can go ahead and just use the formulas, but it is good to at least see these examples and realize that there's some clever substitutions we can make. and it will help prepare us for the method of trigonometric substitution. So let's use the reduction formula to integrate, let's say, the integral of tangent to the fourth of x dx. So we're using the reduction formula number 3. So applying that once, what happens? Well, in this case, so let's basically apply reduction formula number 3 with n equals 4. So our integral of tangent to the fourth of x dx becomes what? Well, in front we're going to have tangent cubed x over 3 minus the integral of tangent squared x dx. And then we can go ahead and apply the formula again to the remaining integral. So if we apply the formula again, tangent cubed x over 3, now n is equal to 2, so what comes out? We just get tangent of x over 1, which is just tangent of x, and then we're getting technically another negative, so we're subtracting minus the integral of the tangent. Well, 2 minus 1 is just 0, so actually what we're getting here is just the integral of 1. So you can replace this tangent of 0 with 1, and the antiderivative of that is just going to be x. So we are all finished. We end up with the tangent cubed of x over 3 minus the tangent of x, and then the two negatives, and integrating 1 gives us x plus our constant of integration. And that is all we have to do. So we didn't have to go through any of the complicated substitutions or rearranging things with trig identities. We just applied the reduction formula twice. So maybe I should mention that here by reduction formula number 3 again. And that is that. So again, I guess maybe the takeaway from this section is review your trig identities, because they do come up lots of times in calculus. And if you run into one of these powers of trig functions, a lot of times you can just go back, look up the reduction formulas, and apply those to make sure you get the answer correct, because doing them by hand can often lead to problems that are pretty lengthy. But again, that's it for this section. This is Dr. Lennon signing off.